Hi, we are going to be going over SD-LoRA, which is a paper from iClear 2025. It deals with continual learning in a class incremental setting and aims to achieve a model that has a low loss in all of these tasks. For a bit of background, generally LoRa deals with a single task setting, and if you have to extend it to a multitask setting, then you use a linear mixture of LoRa coefficients. So if you have a base pre-trained set of weights theta, or actually let me call that W to keep it consistent with the rest of the paper. So you have a base set of pre-trained weights W, and let's say you have n classes coming in. Then to get the information from each of these classes, you get a delta W for each class. And you add it onto the base W with a set of linear mixture coefficients alpha. These may be learned through routing algorithms, through inference time optimization. There are multiple discussions on learning alphas, and this paper also talks about them, but our main focus here is on the delta W's. Now specifically, in this paper, and let me take a step back actually. So delta W, since we're using LoRa, will be these low-rank matrices. Delta W equals A into B, where if delta W is an m by n matrix, then A is an m by r, and B is an r by n matrix, where r is a lot lower than m or n, which lets us have fewer parameters in the delta W's. Now the way SD-LoRa is improving upon this method is when we're adding these components in, then they basically have a magnitude and a direction. But in addition to already having that magnitude, we're also multiplying in an additional notion of magnitude through the alphas. So they suggest breaking up the delta W's to get just the direction, and then using the alphas alone for the magnitude. So for a visualization of their proposal, let's say we have a 3D scenario. And let's suppose we have 4 tasks. And each of these 4 tasks give us a delta W that looks something like this. Now, if we have a unit circle, something like this, then just the directions should give us vectors within that unit circle. And once we get in the alphas, then we can get the importance of each of those by multiplying those unit vectors with alphas. So maybe the first task is like not that important. It's that big. And the second task is super important. So in that sense, you get a notion of task importance as well through the alphas. Their background motivation for this is listed right here. They want a rehearsal-free, inference-efficient, and end-to-end optimized method. One thing to note here is that with inference efficiency and this notion of not having task-specific component selection, they're basically saying that since the model that they're creating is supposed to have a low loss in a general setting and is not task specific, there also isn't any optimization that needs to happen during that inference time. When the task comes in, then you're learning that mixture incrementally. For a more sound formulation of what they're talking about, here's how they're dividing up their delta W's into the direction and the magnitude. The magnitude they get rid of and they retain the direction, and then they put in the alphas as the coefficients with the directions of the different LoRa components as the classes come in, as the tasks come in. Their findings in this basically talk about let me see the one that I want to highlight. there we go. Their idea with the findings, one core idea that was new to me, is that the initial tasks played a more significant role than the later tasks. The alpha Ks in those became more and more important as tasks came in during that incremental learning setting. And the later tasks only provided subtle variations, whereas the initial ones were providing more general information. This information is something that they also use to further optimize SD-LoRA through these two approaches that they discussed through SD-LoRa RR and SD-LoRa KD. So RR just generally, the reason why they're doing these further optimizations is basically that as tasks are coming in, you need to store these additional delta W matrices. Let's say we have n tasks already existing, and then a new task n plus 1 comes in. Then you need to store delta W n plus 1, and this keeps going on. So the number of parameters you need to store is just also increasing incrementally. So one solution to this that they suggest is that since the initial tasks end up being more important, you can make these later tasks lower rank. So maybe R1, let's say that's the rank of tasks, the first task that came in. R1 is higher than, as you go on, Rn ends up being higher than n plus 1, and gradually it becomes lower and lower. But even with this, although the rank is going down, you are still consistently storing more parameters. What if you came up with a method that questions whether Wn plus 1 even needs to be stored? This is what they suggest in SD-LoRa KD. This is a knowledge distillation method in which they first check if delta Wn plus 1 is even providing any additional information. In this approach, they will first learn this additional delta W for the new task that came in, and then they check if the existing tasks are already able to represent delta Wn plus 1 through their subspace. If delta Wn plus 1 is already sufficiently represented by the subspace generated by the previously known directions, then it is no longer stored. This allows us to potentially not need to store additional tasks that come in later on. That should summarize the basic ideas that the paper proposes, and I hope that was helpful.